received his BSc biochemistry. I didn't know that, Jason. PhD in reaction methodology from University of Manitoba, and then worked with Barry Sharpless, Scripps, and then started projects with Donald Blackman at Scripps, and then started his independent career at University of California in 2011, and then moved to UBC in 2015. And Jason, are you ready? So today he's going to tell us about his work on automation on, I assume this is new reaction technologies.
It is, yeah.
Yes.
So can you see my screen okay?
Yes, I can. Do you want to test
awesome.
your pointer? Do you have a pointer as well?
I don't. I sort of swing around here.
Yeah,
I will
fine.
do my best to do explained video.
So that's all.
Good morning, guys.
Okay.
Or good afternoon. Apologies for the time difference. Yeah, today I'm going to be telling you a little bit about the work going on in my lab and how it sort of applies in this area of what we've been sort of banging out, known as flexible automation. So just as a quick intro to, I'm here also as a dual hat. I am a associate editor with one of the new RSC journals, Digital Discoveries. This is a platform that not only speaks, again, I'm still rattled over the previous talk because I have a million questions. I'm an HPLC junkie, which you'll see a little bit in here. But one of the key things that we have baked into this journal is a commitment to the open data standards. So in fact, one of the things that we've really done here is provide data reviews, and in fact, open data policy is actually built into the journal itself. So we're really looking for great submissions. We really encourage you to please look at our journal as a home for some of the work, not only in machine learning, data science fused with chemistry, automation. Really, again, looking forward to continue to sort of drive this home. So as a quick high level, if you've never seen work by my group, the way that we kind of stretch the space of mechanistic analysis that also is coupled to hardware development and applications. Primarily, most of our time is in the space of things like mechanistic analysis that you see in the first couple of instances where we're using online analytical tools to deconvolute reactions or basically optimize processes, especially really in the focus of process chemistry, where the information is meant to serve development of new reactions and manufacturing processes. However, we do a lot of work also in the development of new technologies. In particular, the JChemEd article shown here is some work that we did early in the pandemic, where we hacked the Apple voice assistant. I can't say her name, or she suddenly comes to life. And we built a tool that, via using Zoom, graduates or undergraduates, first years, could dial into the Zoom call, talk to the automation, and perform a titration. And what was really important there is it starts to bridge this gap between students that have never seen interacting with computers or automation or automated equipment. They were able to natively drive a reaction simply by asking for actions that would be normal of asking a graduate student to perform those actions for them. In addition, we have sort of a small perspective done by my newly graduated Dr. Melody Christensen in ChemSci. And it's a perspective on when you think about moving to a fully automated workflow, what you kind of have to think about in advance before you sort of do that transition. So really encourage you to take a look at some of those sorts of things. Now, for today, I'm going to talk a bit about hardware development, really to focus on this goal. I'm from Winnipeg, Manitoba. If you've ever been in the prairies, this happens quite frequently. It's also a crime. But this is how I view the world of endpoint reaction development. You're missing so much because you look at the world through a very narrow sort of porthole. And the better thing to do is to look at fully online profiles. So in fact, transitioning from yield only to fully time course type profiles is something that Donna taught me very well, and something we've been trying to elevate by really pushing that standard to get these kinds of visualizations continuously for any sort of system. And again, the team at ROAR is absolutely behind this exact same sort of vision. In the context of what we're calling flexible automation, the goal here is to really take the best parts of things like rapid fabrication, Internet of Things kind of options, and just quickly bring these kind of automated profiles and platforms together in service of building new types of tools for these analyses. We did write a perspective article in Nature Materials about this sort of concept, and really just, again, framing it with how these platforms can come together. And this is both, digital, hardware, analytical kit, and doing that sort of fusion. And the goal, again, is to bring these platforms together in a shorter period of time. What I'm going to talk about today is how we use that sort of concept to build a couple versions of things for online HPLC and deploy it for reaction analysis and optimization. Now, I don't have to spend much time on this because for a previous one, HPLC is amazing. In terms of reaction analysis and time course, it's one of the best tools to put as your first stop for a reaction, because most things will be able to deconvolve. You'll be able to resolve your peaks. You'll be able to get information quantitatively about concentration and time relatively quickly, just because we have different detectors, different mobile phases. It's a great sort of first stop for sort of reaction analysis. The challenge is really moving it from single point offline to continuous online. And there's a number of challenges there, but one of the base reasons that we could demonstrate for why this matters. On the left, what you have is the online profile for the Suzuki reaction, and on the right, the identical reactions. Those are pulled samples that were sit till the end of the reaction and then injected. So the difference between the two really comes from the reaction continuing in that aliquot. If you're pulling samples and aliquoting for offline analysis, one of the challenges you get is that the chemistry continues, or the entire chemistry around the quench can change what the data stream looks like. So moving to an online format has significant advantages. We've done a lot of work in this space. These are sort of different platforms and evolutions that really are meant to sort of take the entire ecosystem of reactions, really focusing on the worst ones. The mantra we always used in the group was that we're not allowed to make the reaction better for the analytical system. In fact, we had to evolve what would be a large stirred tank type reactor, again, more focusing on the process chemistry kind of space, that reactor had to work with an HPLC. So that includes really some of our most advanced ones, such as built-in glove box type systems for pyrophoric and air sensitive kind of systems like you see on the left of the screen. So how this works, we build a lot of our technology around the Mettler-Toledo Easy Sampler probe. For people who've used it before, this is how it looks like in cartoon. It's a probe-based technology that sticks into a reaction. A actuator will drive this pin out, and then a cup will actually interact with the solution phase, allowing you to pick up both components. That can be drawn inside the sleeve valve. It can be quenched at the temperature of the reaction, and then actually drawn off to for offline analysis, or for really any type of analytical kit. There you have a liquid stream that can be used. The value here is that it allows you to do things like quenching at minus 78 degrees or under pressure, but it also allows things like aspiration of solids. So you can take on slurries and other systems that would be difficult to sip from a reactor instead. What we've done, though, is we've paired this with a variety of different tools in between the sample pickup and the HPLC. And really what this is focused on is an idea of inline CSTR and sample management, whereas once the sample is grabbed from the reaction, we can then bring that slug in line through a dynamic mixer. And by controlling that sort of CSTR behavior, we can actually step down the concentration dynamically as we pass it to the HPLC. What this means is the sample slug goes from some nominal volume, whatever's captured at the HPLC, at the easy sampler. And we stretch that out into a plug flow kind of a system where we've actually programmed in along the long axis of that plug flow its concentration. So by changing the delivery volume, we can either choose to take the slug at some front end. We usually describe this as what we call the comet curve, because it has a front leading concentration point, which we can inject from if it happens to be a high sensitivity, or sorry, a sample that we need that high sensitivity, or we can push further out to the sort of tailing end of it to actually dilute it down to get a more dilute sample. So we can adjust dynamically how much sample reaches the column. This also allows us to deal with in situ processing, such as functionalization if we wanted to, or even dilution and dissolution for solids. So this is the big one. The reason that we focus on this a lot is I'm a terrible column chromatographer on the bench to actually do fraction chromatography. I actually evolved my skills around crystallization to sort of compensate for this. And this is what we see over and again is in process chemistry, slurry reactions and solid to solid transitions are the norm. There's a lot of reasons why these are quite valuable. The downside is that sampling these kinds of things and getting an online profile from this while this heterogeneous process is happening is quite challenging. So today I'm going to tell you a story with the hero being Andrew and Yusuke around the development of valbenazine. Now, valbenazine was a molecule coming out of Neurocrine Biosciences. It is made through a sequence of reactions starting with this 4+2 cycloaddition from this alkene, this ketone, and the isoquinoline. However, it has to be derivatized further with a stereocenter. We have to do a reductive diastereoselective reduction and then esterification. So the real key here is we've got to set that first reaction in formation of tetrabenazine. The original reaction published for this that they were using is this isoquinoline plus this protected enone in order to do this 4+2. Now, how we get there, you can sort of imagine it could be any one of these pathways that are either concerted or stepwise, where the individual bond forming reactions can happen in a sequenced way. Why this matters is, remember, at the end, we've got two stereocenters to set in this step, and then that dictates the enantiomer and diastereomer ratio that we get. So understanding which pathway we're moving and where those stereocenters come from allow us to come up with an idea of what kind of mechanism of control we're going to exert if we were to entertain an antioselective reaction condition. The challenge with this is the reaction looks like paint. It's a solid-to-solid conversion needed to sort of drive transmission here. And understanding the reaction mechanism under these environments are quite challenging. So what we did is we built out a system where we can do this separation. What we have here is the online HPLC sampling system I described, and we were able to profile and come up with linear correlations between the signal response and the amount of solid in the system. Interesting thing with this is we were able to transition from, on the very extreme left-hand side of those curves, most of those samples are in solution, and where we have the star, that's where we transition from a solution to a slurry. And we still have linear correlation as we move between those sort of points. So the value here is that we do have sort of correlation, and we can actually track the concentration over time. So this is a typical process of the original one, where we're starting from a slurry and then transitioning through. You can see by the online HPLC that we can see a buildup of the enone. So this shows us that we can reach a steady state concentration, releasing that amino ketone. We also can start to profile things like our byproducts. In this case, it's a diastereomer product that's showing up in low levels. Interesting, though, is right here is where we actually had a crystallization event. So we moved from one solid phase to the product crystallization. And the nice thing is we have continuous HPLC profiles moving through that slurry transition point. So that allows us to quickly go back to this and say, all right, we're probably not dealing with this part, this lower left-hand side of the curve. We have a fast elimination to form up our enone and the steady state behavior against there. So the real value with this is we can quickly profile and disqualify certain mechanistic interpretations. We went through and did some alternative screening, allowing us to adapt our input. So instead of going with our amino ketone, we broke up that fragment back to the base and to the enone. And what we found is under those sorts of conditions, we could actually not only show that now what we're doing is going in with the amino, and I'm just overlaying the previous graph that I showed before, starting with the amino ketone. So in green, you see the two profiles. There's a very big difference between the enone behavior. One, you're dosing in as a starting material. Previously, you're generating in situ. And this is, again, lessons that Donna taught us. When you look at regions like this, where you have vastly different concentrations, but identical kinetics for your products, again, it speaks to you. It tells you instantly that that is not a control point for this system, that in fact you've got these very different concept, but very common sort of chemistry going on here. We were able to actually move this through, and by actually adjusting this ratio between the enone and the amine, though, we were able to much more make the reaction much more rapid. In fact, we were able to accelerate the chemistry to about 5 times faster. So similar concentrations of product in much quicker reaction conditions, just by dialing in certain pH behaviors. And again, this was a survey process that allowed us to was really visualized by the online HPLC. So some huge value here from the point of optimization, and this is coming from a fully slurry transition using online HPLC. The second challenge, though, was now that we had this tetrabenazine as a racemic material, the process that was being used to get to an anti-pure one was actually to carry out a very clean diastereoselective reduction first, still to racemic product, and then a classical resolution using either camphor sulfonic acid or some sort of other chiral-resolving agent. But what it means is, in terms of throughput, you're obviously losing a lot of your material 2 steps into your full synthesis, and actually at your penultimate compound before your final sort of transformation. So there's a big efficiency loss in this, and it'd be much nicer if we could actually look at somehow accessing these material by starting back at tetrabenazine and saying, could we actually make this as an anti-pure? The challenge here is we need to actually maybe look at something like a dynamic kinetic resolution using crystallization on top of it. So what we're envisioning was, is it possible to take a racemic material, couple that to a classical resolution, something like camphor sulfonic acid, to give us diastereomeric salts, where, if possible, if we had a different solubility of one of those 2 materials, and then coupling that to some kind of racemization of that material in solution phase, we now have the ability to fully resolve this, or to transform the material over to this selective diastereomeric salt. Which just, again, that's our mass flow that would be possible in this sort of system. Again, could be much broader than this, but you can start to see the complexity that gets built in. You have many different equilibria, many different KSPs, many different solid phases that need to be managed in this. So just from the perspective of, as a graduate student, looking at this concept of, yes, we could build this kind of point. And again, as a synthetic organic chemist that isn't really fully skilled in crystallization, this is a daunting task. It's hard to say, yes, it would be great if we could build this, but instead of sort of needle and haystack, we want to see if we could enable online HPLC that allow us to study things like the relative KSPs in a very complex system. So it has to be something that we're not segregating, we're actually looking at the live epimerization. Study the racemization, how do we get these things to move back and forth, and finally solid phase compositions as the reaction develops. So to do this, we've upgraded the easy sampler. What we did is we designed this sintered metal filter tip that actually builds and goes along with the easy sampler. What this does is it actually operates as a reciprocating filter. So while the easy sampler pin is extended, you end up with this mechanical action, which creates a void volume, allowing the slurry to actually filter against this pocket. So it's just like acting with a syringe. That push out, because we have a tight seal across the top, creates this vacuum, which then draws in the liquid, excluding the solids there. And that allows you to capture the material in the pin, just like before, but now we're keeping solids out of the analytical phase. What's nice, though, is that as we go through the second action, the retraction step to actually pull that back in, we're actually causing a high pressure action, which actually blows the solids off of that tip. And now what happens here is that clears the fouling. And what allows this kind of reciprocating behavior, the solids do not sort of end up occluding what would be a constant draw. We get a sample by sample evolution, a sample by sample filtering event, which means that we can operate this for many, many hours at a time. So just quickly wanted to show you a profile of what this would look like in terms of developing what might be the classic resolution. We start off on the left side of the graph here, and we dose in racemic material. We see a jump in the turbidity. This is being monitored through some online turbidity measurement or particle track. And we see that the HPLC shows a racemic, so both of the two curves are identical on chiral HPLC. As we dose in the first charge of camphor sulfonic acid, we actually see an increase in solubility. Both of the two enantiomers rise and the turbidity drops, so that's equivalent to a dissolution event. The second charge, that second step up on there at that about 5-hour time point, what we've now done is we've added enough camphor sulfonic acid to create a solid phase. So we actually have a crystallization event, a rise in the turbidity, and now a splitting of the two enantiomers. They actually separate out. And what's happening there is the solution phase concentration of the blue trend drops while the solution phase concentration of the red rises. And this is indicative of evolution of a new solid phase and creation of in this case, 2 diastereomeric salts. So just with a simple online profile, we're able to quickly go through and say, all right, we can titrate in what is the appropriate amount of camphor sulfonic acid to give us our highest resolution. You can see that further doses, we actually hit a point where there's no resolution possible. And it allows us to do a relative solubility measurement very, very quickly, again, on the native system itself. We can actually go through and use the just mass balance to basically calculate out what the solid phase EE should be based on what we're missing. So the measurement value we're doing is the solution phase concentration by chiral HPLC, but by understanding what the total response factor should be plus the amount of material in the system, we can make an estimate of the purity of the solid phase as well. This allows us to evaluate conditions quickly and say, you know, did we do our job if this was just a normal filtration event without actually having to access or address the solid phase. This also allows us to quickly go through and create very complex solubility profiles. So in this case, what we were able to do very rapidly was to create a profile of our both metastability and solubility across a whole variety of different binary solvents. In this case, it was an acetone water mix for this material, creating us a surface to allow us to know where to operate on this. So it's very valuable in the sense that, especially in this online technique, we can actually program loops where solvent addition and temperature exchange can actually be driven by the online HPLC itself. So we can actually use something like an EasyMax platform to actually inform what it decides to do next in terms of when to dose or other components based on the HPLC itself. So this online point allows you to actually script this and build these kinds of curves with, again, look ma, no hands kind of part. So we had the first part. The challenge was that, okay, we had this camphor sulfonic acid type salt. The problem we found, though, was that there's actually a new solid phase that was not known here. In fact, going through the screening, we were able to identify that there's this binary phase with both diastereomers and camphor sulfonic acid present. And the challenge with this is now we have this, especially at the high concentration limit, we no longer have something as simple as 2 different discrete solid phases we're trying to expand. We actually have 3. So there's now a very narrow concentration window where we can get the single camphor sulfonic acid salt that we want at very high solution concentrations. It's possible to actually nucleate this new phase made up of basically racemic material, both of the 2. So this seriously complicates sort of a single dump and pour. And more importantly, that specific sort of binary or the racemic solid phase would nucleate if we were trying to take a batch of material of both the racemic tetrabenazine, heat it to high temperatures to reach these high concentrations, which we normally what we need to do this racemization. So we're starting to have a problem where the racemization itself has to happen under conditions which are actually orthogonal to the best crystallizing conditions. And we'll come back to that in a second. So we want to focus next on this racemization. So if you remember how we do the formation of tetrabenazine, it's by that sort of 4+2 cycloaddition. The racemization or polymerization at this first center is pretty trivial. It's next to the ketone, so simple protonation, deprotonation will get you there. The harder one is the second center. We actually have to flip both of these stereocenters. And in order to do that, we entertain sort of something that would look like a retromonic kind of a pathway. That it's possible that if the reaction were to sort of open that CC bond and close again, this is what you'd see. And we've actually have some data which shows that this is probably what's happening because we can actually isolate and characterize this aminium kind of intermediate. So understanding how we might do this, remember we're operating under crystallization, what would be like an acetone water system, but the temperatures that looked like we needed were far higher than what the boiling points would allow us for those sort of solvent systems. So we start to look at a vapor tech to screen this. So by passing through a racemic starting material and then varying both the residence time and temperature, we're able to show that it's possible to sort of get some racemization happening, not a lot, but enough at these kind of 100 to 110 degree ranges in these kind of acetone water systems. So now we're into a phase where we almost need a pressurized reactor, or again, reaction in tube, in order to get this together. So what we entertain now is this thing where, again, we've got orthogonal demands for our process conditions. We, we need epimerization temperatures in this kind of 100-degree range. We need to operate in this acetone water kind of range. Again, that goes against the kinds of racemic solid phases that we would normally get in a batch. And then the best sort of crystallization and behaviors is in this sort of lower 10 to 15-degree range for the crystal phase that we want to sort of behave. So what we decided to do was, instead of having a single batch crystallizer, we wanted to split this up into a 2-reactor kind of system. One's job is to maintain the solution phase concentration. So we could set up a slurry at some temperature, which we're controlling the solution phase concentration of our material based on the KSP of that first sort of feeder reactor. Meanwhile, we can use a second reactor, which actually holds on to the crystallization condition. So this is going to maintain where we have the diastereomer that we're looking for. And then by circulating the solution phase between both of them, that's how we can sort of create both fed material in this kind of double CSTR kind of a setup. Most importantly, the return line, after we've dropped off material and crystallized, we use inline racemization, so a plug flow kind of reactor, to reset the solution phase. And that allows us to go back to the warmed reactor, pick up material, and then drop it off again. So overall, this was our sort of scheme. And again, this is the kind of thing that you say, yeah, we're going to go and build this. And if we didn't have eyes like our online PAT to do this, this would be a very challenging engineering proposal. So the best part about I can say about this is having something like the online HPLC tools provides the braveness necessary to sort of jump into this, especially if this is not your sort of area of expertise. And the graduate student responsible for this, Andrew Cooker, is an absolute hero. But absolutely, I think his feedback from this was having the ability to sort of visualize live what's happening really, really helped. Overall, let me just quickly jump in. The reaction works. So by pulling this together, we're able to show that if we don't have the mass transfer or the racemization going on, we can show that the solution phase of the diastereomer we want is maintained, where the turbidity is moving from one flax to the other. So net mass transfer does occur. If we go through and turn on a racemization, what we get is this drop in initial concentration in the cooled reactor, showing that we have sort of maintained a certain solid phase, and this continuous decrease in the other enantiomer, the one we're trying to ablate. What's happening there is we are getting racemization in line. So in fact, we can extract the rate of racemization for our overall system through this. So just very quickly, and I apologize for running a little long on that point. I hope I'll be able to show you that this combination of these different PAT brought together by this principle sort of flexible automation really allows us to very rapidly put time down and optimization on these systems. Again, it's a combination of really these guys. If it wasn't for the ability to have this amazing team of computer scientists, chemical engineers, and just very, very creative and brave souls. In particular, I want to highlight right in the middle there, blonde hair. This is Melody Christensen, now Dr. Melody Christensen. She actually just defended 2 days ago after breaking her foot and yet still getting on a plane and still defending. And it's that sort of tenacity that absolutely inspires me to keep doing what we're doing. So again, with that, thank you guys for your attention, and happy to discuss any other points.
Thank you very much, Jason. It's always very, very enjoyable. So the floor is now open. So just to remind people, please put your question in the chat box. So I have a very obvious question to ask. So
yes,
really like the kind of orthogonal method they're using in your work. So on the data side, how do you actually consolidate all the different types of data format? I mean, what's your solution?
Yeah. So
thing going through as well. So
no, a couple different answers. So right now with the HPLC, we've used some simple Python packages to extract right from the .d files from a chem station point. In fact, so we've been working with Toledo over the last couple of years. In fact, also Second Hat, we've actually a startup now taking this technology over to what would be a full sort of out of the lab prototype. That uses an extraction tool that then drops it into an IC type platform. So all the HPLC data lives in the eye control of the IC kind of world. So it's moving from HPLC into sort of a non-common sort of data stream. And all we did is really say, look, any HPLC format is some kind of an XY data system that can then just be represented as a trend that we're then extracting well, as an array. But you're right. This is why, again, I'm so excited to see the development and of things like the Altrip format, because that is the future we need to do with all this, right? Like it's that data information piece that requires that sort of open access to the things, especially in online format. We need to do this. We have, depending on which system we're dealing with and what point, we've slowly getting better and better at doing that extraction to get to that point where we can, you know, do these manipulations. But really, it's still at that point where if you can't get direct access to the files, worst case, conversion of your signal to some kind of XY data stream into a into some kind of an array or into a Panda, you know, frame or something like that, and then we jump into it for Python. So it's still kind of ad hoc.
If your data output is already in kind of digital format, it's fine. I'm just looking at the crystallization that you've done.
Ah, yes.
You have images. How do you then?
Yes.
Handle
Well,
that?
it's same, right? Like the nice thing there is images are just pictures, and pictures can be trained, right? If we can get an image recognition software to tell the difference between a Chihuahua and a blueberry muffin, we can tell the image recognition system to discriminate between types of crystals. In fact, we have other programs in place now where those images are phenomenally rich, provided you have the right ML visualization tool layered on it. And we have some programs that we hopefully very soon can discuss about that sort of image recognition to information extraction kind of layers.
Right. So do you have more specifically a package that will allow you to say monitor the growth of crystal in real time then and map it onto your?
Exactly. Yeah. Basically, it's just trending. It's taking visual data and turning it into a trend, which then becomes actionable information. Exactly. That's exactly what we're after right now.
Okay. When can you talk about that?
Very soon, I hope. Well, right now I can share. Wow. So the good news is, so we do have a little bit of stuff out right now. We have there's an open on archive. We named this vision tool Hindsight. Again, I do not take. It hurts me to say it every time, yeah. But the students loved it, and it came out in 2020. So it's called Hindsight. And what it is it's an aggregation of sort of webcam or image-based tools to action. So that's the initial one was an image analysis point, but we've now started to build in vision deep learning models to actually take those into, again, signals that can be injected through OPC UA or whatever into sort of other components.
Right. Okay, so I think what follows now. So thank you very much, Jason. Again, a virtual round of applause for